I'm Domingos. I'm also known as DMA and appreciate when I'm called DMA. Today's topic is logarithm. But before, I would like us to see a bit of introduction in logarithmic function. Let's learn together and have fun. Logarithmic function has the form of y equal to this small lg, ax, and bx. We read y equal to log of a of x to the base b of x. That's how we read. So this is the short form, the characteristic of a logarithm function. So a of x is called argument, and the condition is that a of x it has to be a positive number. It can't be zero there. We cannot put zero there. No, you can't put zero. And b of x is the base of the logarithm. So the base has to be a positive number, as we stated here, but it can't be 1. So any positive number except 1. So those are the conditions that we have when we're dealing with logarithm function. Okay, example, we have y equal to log of x to the base 2, f of x equal to log of x to the base x minus 1, and etc. We could have plethora of examples. The most important is us being stick with the introduction of what is a logarithmic function. Okay, now we can discuss logarithm of a number. But before, it's better to give introduction of the logarithm of a number in its mathematics view. For example, let's consider we have log of a to the base b to be equal to y. Let's say log of a to the base b is equal to I. The condition states that this is equivalent by saying that the base to the power y, b to the power y is equal to the argument. This is by definition. So that means by definition, log of a to the base b equal to y, we can transform the logarithm equality into exponential. And the way of solving exponential equation we discussed in the previous video. So if you didn't watch, please watch the exponential equation and come back here. Now let's see logarithm rules. Logarithm rules are important to determine a logarithm of a number or when you're solving logarithmic equations. Okay, rule number 1 is also known as by definition of a logarithmic equation. Okay, in rule number 1, we have log of a to the base b to be equal to y. This is the logarithm way of writing, but this is equivalent as saying that b to the power y to be equal to a, which is the argument. So this part here is equivalent to this part. So when we're solving a logarithmic equation, we can consider this property by remembering always that log of a to the base b, if it's equal to something, then we can say the base is to be equal to that expression and equal the argument. Okay, rule number 2. If the argument and the base of a logarithm are the same, then it's always equal to 1. Even if we apply this rule, this will be satisfied. If we apply this rule, we are going to say the base here to the power y, so a to the power y, which is 1, equal to the argument a. So a will be equal to a. So it's verified. That's why we say that the logarithm of a to the base a is 1 when the argument and the base are equal. Property number 3. This is the main base. This is a power. This base has this exponent, which is also a logarithm. A to the power log of a to the base a, it's equal to b. In other words, when the main base is equal to the base of the log, then the answer is only the argument. For example, let's say we have, let me change the marker. For example, let's say we have 2 to the power log of 3 to the base 2. Since the main base of the power is the same as the base of the log, then the answer is 3. This is equal to 3. This is what this rule says. Okay, log of a is equal to log of a to the base 10. Usually when we're solving this type of log, we call decimal logarithm. Why is it decimal logarithm? Because the base is 10, but we don't usually put 10. So whenever you're solving any type of exercise whereby you didn't see the base, that means there is 10 there. That means the base is 10, that's why we call decimal logarithm. Decimal comes from this base 10 here, decimal logarithm. And rule number 5, log of b to the base Euler. This e here is Euler. So this is equal to ln b, ln of b, which is called natural logarithm or the logarithm of Neper. It was a scientist who created that. And rule number 6, log of 1 to the base a is 0. This rule says that when the argument is 1, no matter the base, this is always equal to 0. And we can quickly demonstrate it by applying definition. When there is 1, we can say it's log of a to the power 0 to the base a. Okay, this is log of 1 to the base a. This is log of a to the power 0 to the base a. A to the power 0 is 1. Okay, now applying rule number 7. Rule number 7 says log of a to the power n to the base b, we can send the exponent of a at the back, multiplying the log. That's why we have n times log of a to the base b. So applying rule number 7 here, we will have 0 times log of a to the base a. Log of a to the base a is 1, we know for sure, from rule number 2. So that means we will have 0 times 1, which is 0. So that's why we say log of 1 to the base a is always equal to 0. Property number 7. In property number 7, as I was saying, when you have log of a to the base n, or log of a to the power n to the base b, you can send the exponent n at the back, here multiplying the log. But why we can't have mistake by saying that 8 is equal to 7. No, those rules are totally different. Here n is the exponent of the argument, here n is the exponent of the log, which is different. When n is the exponent of the argument, you can send at the back multiplying. But if it's the exponent of log, you have to say all the log to the power n, because n is the exponent of the log. Okay, rule number 9. Now let's say, compared to rule number 7, now let's say the exponent is not in the argument, is in the base. You can also send at the back multiplying. But the difference is, in the 7, you send n multiplying. But in the rule number 9, you send the inverse of that number. So if it's m, it goes 1 over m. Let's say it's 3, it goes 1 over 3, and so on. Rule number 10, log of a to the base b plus log of c to the base b is equal to. When you have the sum of two logs, addition of two logs, first of all, the base has to be the same. That's why we have b here and b here. When you have addition, then you multiply the arguments. That's why we have log of a times c to the base b. If it's subtraction, then you keep the base and you divide the argument. That's why we have a over c. Another common rule also is number 12, which is said to be the change of base. This is known as the change of base. We have log of a to the base b. You can implement a new base by saying this is log of a to the base c over log of b to the base c. You'll notice that the base here is the same as the base here. So here is c, here is c. So that means the new base has to be the same on the numerator and on the denominator. So for this log, the base is c, and for this log, the base is c. So the base here becomes now an argument in the second log, and the argument here becomes the argument on the log that is in the numerator. So we can also write like this. Similar to this one, I could write 13 comes from log of a to the base b. We can say that it's 1 over log of b to the base a. We can invert, like if a is my argument, b is my base, then I can say it's the inverse. It's 1 over. Now I change the order. A becomes my base and b becomes my argument. So this is also valid. There could be more rules, more properties, but those are the common ones. Now let's solve some examples based on the rules that we just discussed. Okay, first one. It says to find the logarithms of those numbers. Okay, we have in the first one log of 64 to the base 2. How do we do? The easiest way of solving this exercise is by writing 64 into the base 2. Okay? So if we write 64 into the base 2, we will have log of 2 to the power 6 to the base 2. 2 to the power 6 is 64. And one of the rules says that if the argument is a power, we can send the argument exponent at the back multiplying. So we'll have 6 times log of 2 to the base 2. Look, this base is the same as this argument. It's that rules that say when the argument is the same as the base, then it's 1. So we have 6 times 1, which is 6. So that means log of 64 to the base 2 is equal to 6. Now the second one, we apply the same principle. Let's write the argument and the base into the same base. Let's write it. We know that 32 is 2 to the power 5 and 16 is 2 to the power 4. Applying the rule number 7 and rule number 9, we have this exponent as we did previously. We send at the back to multiply, but the exponent of the base we don't send as it is. We always say that we send the inverse of this number. So the inverse of this number is 1 over 4 times log of 2 to the base 2. Log of 2 to the base 2 is 1, so we will end up having 5 times 1 over 4 times 1, which is 5 over 4. That's the answer. And here we have the same base, different argument, and they are adding up. The rule says we keep the base and we multiply the argument. So the answer will be log of 15 to the base 2. You stop there. Why? Because you can't write 15 into the base 2. Okay, now this one we can say log of 6 to the base 3 minus this one can be transformed into logarithm. But remember, when you want to transform 1 into logarithm, look at the base of the other log. Here is 3, so that means you have to apply log of 3 to the base 3. Because if you say log of 2 to the base 2 is still 1, log of 5 to the base 5 is still 1. But why I didn't choose that way? Because I know already that the base of the other log is 3. So that will make it possible to apply the rule. Since the base are already equal, now I can divide by saying 6 divided by 3. I divide the arguments to the base 3, and then I will end up with log of 2 to the base 3. I stop there because I can't write the argument into the base 3. So I stop there. And here I apply the same rule, which is sending the 4 at the back. I'm going to have 4 times ln of Euler. This is natural logarithm. So we say that Euler always has a base Euler. So this is log of this Euler to the base Euler. The base is the same as the argument, so that's 1. 4 times 1 is equal to 4. Therefore, whenever you find ln of Euler, it's always going to be 1. Okay, now let's solve this logarithmic equation. So when you're dealing with logarithmic equations, especially when it is in this form, always remember the definition that we gave on logarithm when we had log of a to the base b equal to y is equivalent by writing b to the power y equal to a. So applying this rule here, we can say then that x minus 3, which is the argument here, is going to be equal to the base b to the power 2. So x minus 3 is going to be equal to 4. X is going to be, adding 3 both sides, we're going to have x equal to 7. So that's the solution. Now let's say we have second example. Log of square root of x minus 1 to the base 3 equal to 2. Applying the same definition, we will end up with square root of x minus 1 equal to 3 to the power 2, square root of x minus 1 equal to 9. Since my index is 2, then we're going to put both of the expression to the power 2. 9 squared. 2 is the same as my index, they cancel out, so it's going to be x minus 1. 9 to the power 2 is 81, then x is going to be equal to 81 plus 1, x is going to be equal to 82. Okay, now let's solve this exercise. What do you think? Think with me. What would you apply if you have this type of, it's logarithmic equation, but it's also exponential equation. If you can see, exponential equation, because all this expression is the exponent of 4. So when you're solving this type of exercise, which is mixed, which is exponential equation and it's also logarithmic equation, try first to apply exponential rules. So what we do here first, let's look at our 1. Can we write 1 into the base 4? Yes, it is possible. 4 to the power 0 is 1. So that's first what we do. Four to the power 0. Now the rule says when we are dealing with powers, if the base are already equal, then what is missing is me equaling the exponents. So the exponents will be log square of x to the base 2 minus log of x to the power 5 to the base 2 plus 6 equal to 0. According to the rule, this 2 is the exponent not of the x, the argument, but of the log. So we can write log of x to the base 2 all to the power 2 minus this 5, it's not of the log but of the argument, so it can come to the back multiplying. So it's going to be 5 times log x to the base 2 plus 6 equal to 0. Now what we observe is that we have log of x to the base 2 here, and we have log of x to the base 2 here. We can let log of x to the base 2 to be equal to t. I like t. I like letting with t. So I'm going to have t squared, when I substitute here, minus 5t plus 6 equal to 0. This is quadratic equation. We can quickly solve it by finding two numbers that multiplying is 6 and adding is minus 5. If it does not work this method, then we apply another method. So we have t minus 3 times t minus 2. Because if we multiply 6 and if we add is minus 5. So that means t is equal to 3 or t is equal to 2. Since we let come back now and substitute. So for t equal to 3, we will have log of x to the base 2 equal to 3. Now applying definition here, x will be equal to 2 to the power 3, x will be equal to 8. Now for t equal to 2, we have log of x to the base 2 is equal to 2. So x is going to be this 2 to the power 2. X is going to be 4. That means our solution will be 4 and 8. So if you enjoy, leave your like, your comment, subscribe, and most importantly, share with your friends.